Okay, I think we can start this second session of the morning. I'm Dario Geraci from the University of Pavia. I'm going to chair the session. There will be two invited presentations. The first one will be given by Savona on variational approach to the non-equilibrium states, matrix products operator and beyond.
Thank you very much, Dario. I will join everybody in the organization and the witness in particular for this excellent opportunity and for the very nice place. In my talks, I used to gloat about how beautiful is my own place, but I think I skipped this today. I couldn't resist. I mean, my topic is not this one today, but there was so much topological photonics that I couldn't resist from flashing our very recent result, where with my brilliant ex-PhD student Momchi, who's now at Stanford, we show that you can achieve the Haldane quantum effect in a dynamically modulated optical lattice, and this is a well-known concept. On the Kagome lattice, this is the novelty, and thanks to the Kagome lattice, the modulation can be first of the on-site energies or resonant energies of the cavity, and not on the hoppings like all the other proposals do. And also it can be translational invariant in space. So it's a modulation pattern that is periodic in space, and this means that your system will remain translational invariant. We have seen shaking a few days ago. In the shaking you introduce a potential which grows linearly in space, so you lose translational invariance. And this gives rise to nice edge states, topological edge states, which are well confined on the edges and everything. So I encourage you to look up this paper if you're interested. Today's topic instead is about the methods for computing the non-equilibrium steady state of open quantum systems, which is a very today in this conference, it's a very important aspect. I will talk about two methods. Essentially, I have two parts. The first one is about variational MPS approach, and the second part is something very new and very preliminary about the quantum Monte Carlo sampling technique of the density matrix equation. I would like to acknowledge two persons. First of all, Eduardo, who's here and who's my MPS man. So he is the one who does all this stuff. And to a minor extent, I would like to thank also my other postdoc, Hugo, who's not here, but he provided all the quantum jumps, so Monte Carlo wave function simulations that I will use to compare to the other methods. Let me start with this first part. This is now a quite old result. It is 1 year old. I will not be very long with this. So, as we know now, after the many talks and the lectures by Ibrahim, the MPS ansatz is probably the election tool for dealing with many-body quantum systems in one dimension. Okay? And I'm citing just this famous review paper, but there are many others. This is my very pedestrian view of what has been done. So you can be studying closed or open systems, and you can be studying ground state or steady state variationally, or you can reach that with time evolution. And now this has been done. This is the very basic MPS, variational MPS to the ground state. This has been done. This is the time dependent. In several schemes, it's possible to do time dependent MPS of Hamiltonian systems. This has been achieved. The time-dependent solution in MPS ansatz of the equation for the density matrix has been done. We have seen it many times in this conference, and these are two seminar papers that have introduced this idea. And this slot is somewhat not completely filled, or at least it was not until very recently. This slot, so open systems, variationally, they have only been approached at thermal equilibrium, where essentially you search variationally this density matrix. But out of equilibrium, the variational approach to the non-equilibrium state still didn't exist until recently. And the idea is the following: we want to solve this, the second of these equalities, L rho equals 0, in a variational way, not by evolving the system in time. This is now published in this paper last year, and I should point out that ended up doing this in parallel and unaware of each other with a group of American manuals in Max Planck. They published this paper at a few months' distance in advance of us, and you should give at least equal credit also to this work, if you're interested. The aim of the game is always the same. We want to solve the Liouville von Neumann equation for the density matrix, including the Windland terms that model the Markovian come into an environment with some jump operators. And a small technical detail, what we can do is that we can vectorize the density matrix. Vectorize density matrix means you just take columns and you put them all on top of each other, and out of the matrix you do a big vector. Okay? This has an interesting property that if you do that, then if you want to compute operator time density time operator vectorized, this corresponds to this expression here with this tensor product. And if you exploit this feature, then your Liouvillean is now a big matrix, so it's an operator, and it's expressed in this way with tensor products. So this is very easy for calculation. Okay. And then what we want to do is that we want to take the Euclidean norm of L rho, and we want to minimize it, because this object, the square, is always larger than 0. We want to minimize it, and this corresponds to minimizing this quadratic form here. But we may even do something different. We may simply search for variationally for the null eigenvalue, so for the 0 eigenvalue of L. Of course, all this works under the assumption that the Liouvillean is well behaved. This means it has perhaps a gap, and the non-equilibrium state is sufficiently, so it's unique, it's not degenerate. If these two conditions are not fulfilled, then we know that all methods bump into trouble. Then there may be better and more strategies, but we know that that's an objective efficacy. So we will make this assumption. Okay. And then it goes like this. Now we have seen these diagrams a lot. So you can write this vector now as an LPS ansatz, okay, where this is a basis set typically of occupation numbers of a chain. And this has a diagrammatic expression like this. And here I have already isolated the local. So this is contracted on this side, and this is a local density matrix which is defined by this diagrammatic expression. Same thing can be done for the Liouvillean, which now can be expressed as an MPO, so that is a matrix operator. And again, one can single out a local term in this operator, and once you have this, then you can write the equation you're interested in as in a diagrammatic form like this. Here you have 3 empty legs. You have to do the reshape like we have learned on Sunday from Peter. And that's again a vector, big vector again, and you want this thing equal to 0. Okay. So you can what you can do is that you can apply the usual LPS strategy. You take this local problem and you search for the eigenvalue whose modulus is closest to 0, and then you sweep back and forth, and hopefully this should converge to the 0 eigenvalue. In order to test this, we have used a model that has already been published, so that we have the data to compare to. This is a quite famous paper by the group of Jonathan Keeling, where they study a quantum isochain. What we do is that we can add a second next neighbor interaction that I will explain in a moment. Let's take first the case in which this interaction is not here. This is the case which is published in this paper, and we reproduce perfectly the result of the paper. This result, this is a correlation. This is a correlation between next neighbors as a function of the ratio between these two parameters. And you see here that you have on this side you have a ferromagnetic ordering, and on this side you have an antiferromagnetic ordering, and this is the physics of this system. And we compare the variational approach, which are the dots, with the proper dynamics, so with the time-dependent method for density matrix, and the correspondence is perfect. And then the point that I want to make here is that if you add the second next neighbor interaction, then Trotter becomes no longer viable. I'm not saying that it is not possible to solve this problem by time-dependent technique. There are more advanced time-dependent address the problem when Trotter can't be done. I'm just saying that this method can go a little bit farther than Trotter. In this case, again, the comparison is perfect, but now the comparison is the Monte Carlo function simulations that we did separately. So again, this method works independently of course, it doesn't mean that the bond dimension will grow if you have a longer range interaction, but you can use it in a more black box fashion than the time-dependent version. And this is what I want to say. Okay, this is just an example of application. This method is useful, and the point I want to make is that this is an additional tool that maybe is complementary to time-dependent, to MPS quantum jump, and to all the other tools that we have, and may be useful in many situations as an additional tool. Yes?
Can I quickly ask, so for the left plot, how do the matrix and the bond dimensions compare between the dynamic, the Trotter version,
Let's ask the MPS manual.
What was the question again?
Bond dimension.
the bond dimension of the variational approach and the time integration? How do they compare?
The optimal, let's say, the optimal one dimension should be equivalent, irrespective of the method you choose. So your asymptotic state is going to have some, let's say, entanglement spectrum, and how you get to that state, it doesn't matter which method. So the bond state, the bond dimension of the state, should be the same. Doesn't matter which method.
It's a property. It's a physical property of the system where the convergence versus bond dimension. So it's not. It doesn't change as a function between the two methods.
And that happens in practice as well. So
yeah, but actually here there is an advantage because you get away with the error from the discretization in time dynamics. So here there's no Trotter error. So as long as you sleep enough, you converge.
Indeed, here you don't have any Trotter error. But I want to say something about the stability of this method. So the only thing that we did different with the group of Maricarmen is that we search for the zero eigenvalue of L, and they do something which is much more intuitive at the beginning. They search for the minimum of this quadratic form. Okay? And of course, L is non-hermetic, has complex eigenvalues, it's a much nastier beast, whereas the diagonal is positive semi-definite, it is hermetic and everything. So, algorithmically, what we see empirically is that the L version is less stable because of this reason here, but it is significantly faster because you can understand it in terms of bond dimension of the operator, but the considerations are a bit more subtle. I don't want to dwell on this thing now. And the L-Daggerel is generally more stable and well behaved, but it is of course slower because we have a bigger object here. Okay. So this is again you choose which one according to the problem under investigation. One may be more advantageous than the other. Okay, I'm done for this first topic, so I would like to address now the second topic, which is something very, very preliminary, I know of you. Quantum Monte Carlo. Of course, if I say Quantum Monte Carlo in this community, you all say, but come on, this is obvious. Monte Carlo function, quantum jump, quantum trajectory, quantum diffusion. We have Perazzolo giving beautiful lectures today. No, I'm not talking about that. That Quantum Monte Carlo is a way to sample stochastically the quantum fluctuations that are induced by the environment on the system. But the degrees of freedom of the system, you integrate them exactly, or perhaps with the clever answers like MPS. Here I'm talking about a way of sampling the degrees of freedom of the system stochastically. So Monte Carlo Ada separately, David separately. Okay? And this is something that, to my knowledge, has never been tried for this problem. So here's my idea. The real-time dynamics, again, is given by this equation, and the eigenvalues of L, they all have the real part smaller than zero, so that this thing, all the excited eigenstates components here decay, and in the long time limit, you end up just with a zero eigenvalue, which should be the non-equilibrium state. And this bears a strong analogy with the problem of finding the ground state of a Schrödinger equation, so an Hamiltonian problem, by using imaginary time dynamics. Here again, you start from a given state, and the Hamiltonian imaginary time dynamics will kill for the excited states, actually, if you choose this energy shift to be exactly the ground state energy, then this will act as zero on the ground state component here. And so essentially, if you wait long enough, the longer time dynamic will be left, you will be left only with the ground state and with the ground state eigenenergy. Okay, this approach is particularly suited for quantum Monte Carlo schemes. In particular, the class of Monte Carlo schemes that are used are called projector Monte Carlo or Green's function Monte Carlo. The terminology is a bit, it varies a bit along across the different groups. A very old paper where this is addressed is this very famous paper here, a quite comprehensive, this is by separately, a quantum comprehensive recent review is given by Savona here. And now my question is, can we, given this analogy, can we apply this strategy to sample these time-dependent equations stochastically? Okay. And I want to say a few words about the projector Monte Carlo. How does it work? Projector Monte Carlo means if you want to compute a time step with this propagator here, this is called a projector. Okay. The strategy is the following. You try to write this projector as the product of two objects. One object should be a stochastic matrix. Stochastic matrix is just the matrix that propagates a random walk, Brownian motion. Okay, it's positive, it's all everywhere positive and normalized to 1. So it's like a Gaussian, multivariate Gaussian. Okay, and this is what propagates a random walk, and this is the remainder. So this is what it needs for this product to be equal to P. And ideally, you would like this to be also positive. Unfortunately, this is not always the case. This is a precursor of the sign problem in Monte Carlo. Anyway, when you have this factoring achieved, then what you do is that you take the wave function and you sample it with walkers. Walkers are objects that carry statistical weight. And these walkers walk across the configurations in Hilbert space. This could be real space, many-body real space, but it could be any other representation of Hilbert space. They walk according to random walk, which is dictated by this matrix. So you evolve that, and then you have to apply this thing. And this thing inflates or deflates the wave function. Remember, we have an imaginary time. And this you do by correspondingly, stochastically, increasing or decreasing the statistical weight of the walkers. This is one strategy. A better strategy is to branch. So you make the walkers branch, or you make them die, depending on whether this thing is small or big. Okay, and then you loop. And these many walkers will crawl in the Hilbert space, and in time, once you have reached the steady state, in time, by averaging, they should and they will sample the expectation values of quantities on the wave function. Okay, this shift is typically adjusted dynamically, and at the end of the when you are stationary, this shift, which is adjusted dynamically, I will show you how in a moment, will tend automatically to the ground state energy. So this is one of the estimators of the ground state energy. It's not the only one. You can also compute it for the matrix element of the Hamiltonian. Now this object has typical challenges, which are very well known in the Monte Carlo community. By the way, I'm not a member of this Monte Carlo. I'm a beginner in quantum Monte Carlo myself. The sign problem, of which many of you have probably heard, essentially, if you try to sample something which is zero with objects that randomly take positive and negative values, it is proven that the statistical error will diverge in time. And actually, you probably you know that the sign problem, in addition to being a technical problem, it has been proven as a manifestation of the exponential complexity of the exponentially hard complexity of a many-body system. So the sign problem is unsolvable. Otherwise, you win $1 million because there is this mathematical foundation that has a $1 million reward if you solve the sign problem. Okay. There are also other problems like this factoring typically is not exact, it's approximate, and it's really painful to find a good one. Okay. Anyway, this method is now universally applied. It is a lot successful, but the sign problem is discouraging, and you wouldn't apply it to a non-equilibrium problem like ours because you will have a lot of excited states which would carry a lot of sign problem. Okay? Yes?
So the sign problem is usually for fermionic systems.
It is also for excited states of bosonic systems. An excited state of a bosonic system has nodes, as well as in the same way as fermionic systems. No. It's only the ground state of the bosonic system that allegedly has no sign problem, and even there you find papers that show that even there you have some form of sign problem.
If the bosonic system is supposed to be in that approximation, then definitely it won't have a sign problem.
Yeah, but we are not considering close to infinity. Here we would like to use this thing to solve a many-body problem. The bosonic problem is known to have a sign problem in the excited states. This is quite intuitive because wave functions will have nodes as well. Then there are ideas that actually even the ground state, a very simple example, if you have a potential with a high barrier, this will correspond to a teeny tiny wave function even from the ground state. That object is close to zero, and that object is extremely difficult to sample in Monte Carlo way, and so it will generate, so to say, a small brother of the sign problem. So it's really almost only present.
So you mean this is super strongly correlated?
Strongly correlated, of course. This would be the scope. The scope would be to apply in that context. Now, the good news is that very recently, in 2009, a bunch of chemists, being a bit next year, a bunch of chemists have developed a variant of projector Monte Carlo, which is considered quite a breakthrough, which is called the full configuration interaction quantum Monte Carlo. Configuration interaction is the chemist's way of configuration interaction. They compute molecules, they take molecular orbitals, amplify molecular orbitals, build Hamiltonian matrix with Coulomb matrix elements, take 1 million of them, and then they diagonalize. Okay, so this is configuration interaction. This can be done in Monte Carlo way. This method is very interesting because, well, first of all, it has a different strategy. There are no random walks. The random walks are replaced by a spawning annihilation scheme that I will explain in a moment. And allegedly, this scheme doesn't solve, of course, but alleviates significantly the sign problem. Okay? I say allegedly because if you object this, I will not lead a fight now to defend this statement. But empirically, it is what you see, and even famous Monte Carlo physicists agree with this statement here. You can have a look at the papers. And the good news is that it works also for excited states, for spectral properties, and also for finding temperature by sampling again this density matrix. Okay? So the plan is to use this for the fluid von Neumann dynamics. Let me explain briefly how it works. So you want to use the projector. Bad news is that this method works easily only if you take the Euler approximation of the projector, which we know it's a Krafft approximation. We have a time-step error and everything, but you have to control this. But it's the straightforward way of applying this method. So again, you express the wave function on a basis, and the basis elements are called in the chemist's language configurations. They are basis elements. And these amplitudes then are governed by this equation. This is the same as before, just for the amplitudes. And now you sample the amplitudes with walkers, and these walkers take only discrete values, plus minus 1. They are signed. Okay? So on average, this quantity here is just proportional to the number of walkers times their sign. If you do that, then the algorithm works like this. It's made of 2 steps. The spawning step, again, I'm telling you walkers here don't walk. I keep calling them walkers because I like the name. But they don't walk. A walker can spawn another walker to a child configuration according to this probability, which is defined like the matrix element here. And if the spawning attempt is successful, it is sampled in Monte Carlo fashion, then for each successful spawn, you define the sign of the child walker as the sign of the parent walker times this sign. Okay? And if you think of it, let me give you the second step. This is crucial. This is called the annihilation step. Once you have done this for a time step for all walkers, then walkers that have opposite sign act algebraically. Okay? And this is crucial because there is not such a thing in the conventional Monte Carlo sampling strategy. Okay? So they disappear, which means that on a given configuration, only walkers with the same sign survive. And this is why I am writing this expression here, because these things will all have the same sign sitting on the same configuration. Okay? And then you repeat this. You loop over this for many time steps. You can improve a lot of this algorithm, like for example, choosing only one child configuration randomly at each time step, which requires to handle the diagonal process separately. There are a lot of technicalities in here, but essentially, this is the elemental version of the algorithm. And the initial step, once again, is what is considered as the element that improves a lot of the design problem. So my proposal is to apply this to driven dissipative systems, and so I call this driven dissipative Monte Carlo. I vectorize density matrix. I have additionally to use a real imaginary representation of it instead of a complex one, because I don't want complex numbers, but this is very easy. You can write real imaginary separately. So now the Euclidean is a matrix, and this is the equation. Same as before, you have this shift here. Okay? And now you apply the algorithm. You apply the algorithm as you have seen, and this shift is updated every m time step according to this formula. This is very standard in Monte Carlo. You find it in seminal works of 30 years ago. Okay? Essentially, when you reach a maximum number of walkers that you have chosen, then you start applying this update strategy with a number of walkers here. And this gives you, on average, a constant number of walkers that has been reached. Okay? And the idea is that when you are stationary, then this S updated in this way will converge to 0, because 0 is the eigenstate, the eigenvalue that we are looking for. Once you have reached the steady state, then you start sampling quantities, and quantities can be sampled like this. So you have to take a time average instead of just an expectation value, because this is how Monte Carlo works. You replace average in time, you use average in time instead of expectation value. So you have to average the numerator and denominator. The denominator is important because here the base is not normalized, because this is a feature of the Monte Carlo in general. Even the normal wave function is not normalized, it goes everywhere. So you have to apply this form. Okay? And there are again other technical details. You can improve using this initiator method, which prevents walkers from diluting too much in the deeper space. You can use binomial random numbers for moving postponing the walkers clockwise and making it more efficient, and so on. Now let me show you just a very preliminary result, which is a proof of principle. Okay, it's not by no means. I mean, this thing is not yet at the stage where it can be used efficiently for problems, real world problems, but it works. Okay, this is a proof of principle. So let me solve the half-core boson chain with repulsive first-table interaction and periodic boundary conditions, which maps onto the XXZ model. This is the famous review paper by Terry and Marty, if you want to look it up. The Hamiltonian is this, with drive and dissipation. And dissipation is given by the usual equation. Okay? There is this next neighbor interaction, which is the non-trivial part that gives you many points. I will be solving the system with 12 sites. It's small because everything here is under development. 12 sites is just about what you can't solve on a PC or a computer with a density matrix. Of course, you can solve it with one jump very easily, and I will show comparisons. And these are the parameters I will vary the U around the value of J to demonstrate some well-expected physics. This is a typical Monte Carlo run. I'm plotting here on top. The blue curve is the number of walkers, total number of walkers. It increases. You start from the ground state. The number of walkers start increasing because the shift is negative. The initial value of the shift is negative, and then it saturates to some fixed value that you decided, and there it stops because of the update expression that I have shown. The red is the number of occupied configurations. So this is is about, at steady state, it's about 10,000. Remember that this density matrix has 16 million matrix elements, so we are using only 10,000 basis elements at the time to sample this object. So this gives you an idea of how Monte Carlo works. It just uses a very small part of the Hilbert space, but it roams around and it samples everything. And this is the value of the trace, just to show you that this is also varying. Okay? At some point, this is the shift. Here you start updating. The shift now oscillates a lot because of that formula. And at some point, it reaches zero. When it reaches zero, it means that you have reached a stationary state. Then it stands around zero, fluctuating. And it is starting from here that you start accumulating your expectation value, the statistics for your expectation value. And these are the results. As I told you, they are very preliminary, so they are far from being so statistical error is still very big because I a bit miscalculated what I would have been able to present here by submitting the abstract when it was submitted, but never mind. So this is the occupation and the average occupation at each site for a particular value of U. The red is the exact and the blue is the quantum integral. But it's the scale, nevertheless. I mean, these bars are big, but they are not huge. And this is the G2. So the side, so the second order correlation function. You see, for this value, a typical anti-bunch to the next side, and then it goes to 1. And here you see a typical Monte Carlo bias. So this is a typical feature that occurs if you don't apply the very many tricks that Monte Carlo requires. And this is now a plot of the next neighbor, so of this value here, okay, as a function of U. And here you see that you see quite expected physics of this object that goes from large to small as you increase the U. And again, here you can see a bit of Monte Carlo bias, which means that here the system becomes a bit more correlated, and so you need a bit more walkers, which I didn't use to sample this part. Okay, but all in all, the result shows that the potential for becoming a good method is there. It just needs to be improved. And improvements are these. First of all, you should know that if you take a textbook and you try to write a quantum Monte Carlo from a textbook, it will never work because there are a lot of very, very clever tricks that only the experts know, and I am learning very slowly these tricks. First of all, you have to use a very effective problem-dependent strategy for important sampling. Important sampling means try to guess the solution and give more statistical weights to the points in the Hilbert, so to the configurations in Hilbert space which you know will be big. And those that are negligible, you have to try to not to sample them. Okay? And this is there is a whole world of approaches to this important sampling that one has to refine and apply to the problem in question. Another important thing is semi-stochastic approach. Another feature of this configuration interaction quantum Monte Carlo is that it is suitable for the semi-stochastic approach. Semi-stochastic means take a small part of the Hilbert space, I don't know, 10,000 objects, and integrate exactly. The rest you integrate with this strategy and you combine the two together. And this can be done thanks to this particular algorithm, and it improves dramatically the statistical error. And typically you have to choose the core space for this exact integration in a way which may be real subspace or something. Okay, you have to choose a relevant subspace. And then, of course, this may be still improved using a smart quantum correlated basis set. Here I'm using the totally non-correlated basis set, which is not very smart. But there is one work, I searched hard and I could find only one work where MPX, for example, is combined with a projector Monte Carlo technique, just in this spirit. But this is not the configuration interaction Monte Carlo, it's still the old strategy of MPX. Okay? And this is just for Hamiltonian, and it is also for Hamiltonian problem, so it's for ground state, which presumably will be more robust versus sign problem. And finally, of course, you need to implement large-scale parallel version. This full configuration interaction Monte Carlo is very easy to be made parallel. Only the annihilation step requires communication processes. And so I'm looking forward to this. For the moment, my book is serial, but I have a fresh blood in my book with the good features, a good combination of physics skills and coding skills to do this, hopefully, in a very good way. Okay, and if you do this, I'm confident, because of the success of Monte Carlo closed medical system, that this may be a very powerful additional tool for addressing the problems we are all interested in. And with this, I'm finished. So I presented these two methods for addressing the non-equilibrium steady state. They are both quite promising. The second one is a bit preliminary, but I hope to be able soon to get to a result that can be communicated. And so with this, I'm finished, and thank you very much.
So for this last presentation, there are questions.
But one of the main advantages of quantum Monte Carlo usually is that it can compute also integral with a very large dimensionality.
Yes.
In your case, however, as far as I understood, you always rely on the diagonalization of the Euclidean. Is the case? No. So
My Euclidean. So one of the features of this, and in general of all Monte Carlo, is that you have to be able to compute Euclidean matrix elements on the fly.
okay.
You don't want to store anything. So you don't diagonalize. Not only you don't diagonalize, but you don't store. The only thing that you have to do is that you have to. So it's the. I'll show you for the Hamiltonian, but it is the same. You have to be able to compute these objects, which are just matrix elements, on the fly.
Okay.
Okay, and these give you probabilities. And the storage, so the idea of how well this works is given by the fact that this particular problem has 16 million matrix elements, because it is 2 to 24, and I'm sampling them by having only 10 to the 4, so 10,000 non-zero at each time step. But these 10,000 change, they grow around, okay? And of course, this number becomes bigger if your system is more quantum correlated. At some point, it becomes non-viable, of course. But this is a general property of all methods. I mean,
No, I was wondering instead this how large dimensionality of the Hilbert space you can get.
So if you read the papers by Alianami, who is the person who had this idea and started the method, he has some papers where he does the many electrons in a box, and nominally his Hilbert space is 10 to the 109 vector states. However, the problem is not so much correlated, and therefore you can still find a very nice ground state energy. Molecules, for the chemists, are strongly correlated, but in comparison to our strong correlations, those molecules are very weakly correlated. It's just a matter of orders of magnitude. Okay, so that's why this method is particularly suitable in quantum chemistry.
Can you foresee where are the advantages of this Monte Carlo mechanism to tensor method approaches?
Well, one advantage that I see is that, first of all, this method works in the same way no matter what dimension. This method you just have to define a discrete basis of your Hilbert space. Then you forget about everything else. So algorithmically is orders of magnitude easier than tensor network. In one, I wouldn't use. I am using this in 1D, but I wouldn't use this specifically for 1D problem once I want to really solve a problem because I have a better way to do that. But dimensionality is certainly an advantage. I don't want to say that Monte Carlo is a black box, because it is not a black box. I mean, if you really want to solve a problem, you have to take care of all those points which are problem specific that I listed. But still, you have strategies to do that. For example, for the important sampling, I'm now experimenting with using as an important sampling function the Woods-Wheeler solution. So to try to sample the full solution using statistical weights that are taken from the mean field solution. supposed to be closed, and then you are supposed to go search at the right places, more or less in statistics. But the advantage of Monte Carlo is that in principle, it's exact. In reality, I mean, you have seen the error bars, but in principle, you are not doing any correlation length approximation, nothing. The only problem is that if you want the statistics, you have to make the simulation bigger and bigger. But so in the end, it scales exponentially. The chemists claim that it scales weakly exponentially, whatever this word means. It's written in many papers. But so the idea would be that given a difficulty of a given problem, this Monte Carlo is able to give you a very good prefactor to the exponential component. That's the idea.
So I have a question. So talking about the initial, say, the guess for the surface where to work. So in the method we are using
for the semi-stochastic.
Yeah. Okay. So in the method using the 2D corner space normalization, we have already this.
I was thinking of this 2 days
probabilities.
ago. You may start from your solution and improve it with this strategy.
Because we were wondering, since we have a lot of probabilities already calculated, we don't fully exploit the information about the probability spectrum.
The end point of your calculation would be a very excellent starting point for this strategy. Because you may take your basis vectors, for which you know all matrix elements already, because per definition your method stores all the matrix elements. And then you may use that for this. I mean, there can be refinements.
No, for example, just to give for a problem where there is a Hilbert spaces 10 to the 6, 10 to the 10, the basis we find is around the 4,000. So there's a big jump. But then there is a limitation in memory that could be lifted if really stochastic implementation.
Yes, that's possible. But there is no magic once again. So if the quantum correlation increases, so all these parameters will increase. Bond dimension depends on network, your M, and the number of walkers here. There is no magic.
Is it possible to generalize your method to find the other eigenvalue of the Revelian?
Yes, I mean, I didn't do that, of course, but there are, I also cited the paper here. Yes. I didn't cite it. Okay, never mind. So this is what I cited, but I can show you a paper where they were excited state. You can also use it for sampling spectral properties directly. You can use for a lot of tasks, but essentially there is an excited state version of this algorithm, which works. At least they demonstrate it.
If not, let's